My name is Rene Smeets. I work for KEMA Labs, being part of the Chessie Group, and the next 15 minutes I would like to share with you a few words on what our work in work package 10 of the promotion project was related to development of the standards for HVDC circuit breakers. So the slides I'm going to present you consist of a few parts. As you know, HVDC circuit breakers protects HVDC grids. We will give a very little basic background information about that. Then I like to give a little bit more details on the standardization structure we are going to follow, or we are following already. When we speak about testing and test requirements of circuit breakers, it's quite important to know what the stresses they face. So first we will very briefly look into what type of system-related external stresses these devices are exposed to. And we did, and also other work packages in the project did a lot of simulation studies related to that. It's not my intention to repeat this, even not to go into depth in this. You can find this on the websites. I will also very briefly touch the experimental studies we did on the internal stresses, because making standards means you need to have a thorough knowledge of the stresses to which devices itself and internal components of the devices are exposed to. And that will bring me to test requirements we have defined in the promotion project, and which we are bringing forward, of course, to the IEC. Speaking about switchgear in HVDC stations, of course, since many years, since the beginning of HVDC, a very large number of switchgear is already known in DC. We made a very good inventory in the secret technical brochure 683. And of course, it's not my intention to discuss all of them. What I just want to briefly point out, we have identified in that stage already 24 different types of HVDC switchgear, which are disconnectors. They might be earthing switches. We have high-speed earthing switches, we have transfer switches, we have bypass switches, but the real device which is not actively active in real projects is DC circuit breakers. The photos you see give some very few examples of how these switchgear, these switches look like. So what all these switches have in common is that they are not able to switch off short circuit current. Circuit breakers can do that. But circuit breakers you will need only in the case you are speaking about HVDC grid. Well, up top you see one example of DC switchgear, the 320 kV DC GIS switchgear, which is going to be discussed in detail by Uwe in the next one. So speaking about HVDC breakers, these are devices we will need in future HVDC grids. Well, what is the structure of standardization of HVDC switchgear? I will not run into too much details. I think Mark Waldron will do that in an hour or so. But what we did is we use a Chinese draft document on common specification of HVDC circuit breakers and a number of Chinese standards on HVDC switchgear as a draft. Then, of course, we looked quite closely to what IEC standards on AC circuit breakers are going to teach us. So these are the 62271-100 and the -1 standards. So they form the basis of a new standards. We look for the definition. Rene has mentioned that already. We look for the definitions to what has already been intensely discussed in the secret working group. And then we will use examples of tests we did in promotion as input on how future test requirements might be. So the track we are going to follow is from the promotion to the working group 64 in IEC, which is going to define a draft standard for HVDC breakers already this year. Speaking about HVDC breakers, why do we need them? As you might know, there is a need of evacuation of a very large amount in the hundreds of gigawatt range of offshore wind in the North Seas by 2050. And a clear candidate to do that is, of course, HVDC, although there's a lot of discussion on power to gas these days. But let's assume we are going to do that with DC, then that means we need grids for that. Well, the most simple design of a grid you can see here. And what do you need in case you have a fault? So a fault in the DC, well, this is in a line, so this is not in the offshore case, but this is that is why I would like to show it. And in case you have a failure on your cable, on your submarine cable, it's essential to disconnect the fault, to isolate the faulted section of the grid, and you need HVDC circuits.
We have a participant who needs to mute. He is talking. Please mute your microphone if you are not speaking.
Yes, please. So we have seen since 2011 a steady growth of concepts and designs of HVDC circuit breakers in the world. Time is too short to run through all of them, but here you can see a few. It's good to mention that some of them are really tested in promotion. So here we see one. Here we see a 350 kV hybrid type of breaker, and by the end of the project, we are going to test a VARC type, a new innovative type of high voltage DC circuit breaker. Well, why do we need to pay such an attention to current interruption in DC? We have AC breakers for a large number of years. The reason I would like to explain you is with a swing. In AC, we have, of course, an oscillating wave of current and voltage. And when I'm in a room, I'm always asking who of you can point out what is the best opportunity to stop the motion of that swing. Well, here I'm not going to ask that, but I think quite a few of you would have answered me. That is in the extreme position of that swing. So we can stop the motion because at that moment there is no energy in the grid. So that's the basic advantage of AC. There is at the zero crossings, there is no energy in the grid. Well, in AC, of course, in DC, that's of course not the case. We have a constant motion. If you transfer it to a mechanical analogy, we have a constant motion, and what DC breakers need to do, they have to stop that motion, and they have to do that in a matter of milliseconds. So they have very little time to do so. I always like to show what the effort means by transferring the electrical challenge into a mechanical challenge by saying if we have a 15 kA short circuit current in a 100 kilometer DC line, that means we have stored 11 megajoules in that fault, in that line, which means from a mechanical point of view, we face the same issue with our DC breaker as stopping a 30-ton train, which is running at 100 kilometers per hour in a few milliseconds. So that means you must have a buffer who is going to do that. And if the buffer for the train is not going to do the job, you see events like this. So we try to define the critical stresses on HVDC circuit breakers, which means what happens when there is a development of a fault in a DC grid. We have a steady state current, which is neatly flowing here, and at a certain point we have a fault, a cable fault. That means a very fast rate of rise of current to a very high range. So that means we must oppose the short circuit by this buffer, by this blocking, and all DC breakers do that by making a counter voltage. So the task is to develop very fast a counter voltage. And based on development of that counter voltage, the current is suppressed, the fault current is suppressed to zero in a certain time when the voltage, the counter voltage, is kept sufficiently long and sufficiently high. Well, after the current is interrupted, of course, the voltage of the system returns and the breaker in its open state should be able to maintain that. Well, the 6 critical stresses that have to be replicated in test requirements are then, of course, the rate of rise of fault current, the internal commutation, the voltage rise, the counter voltage rise, the over voltage withstand, so the sufficiently long duration of that voltage, then the quite important, the energy absorption in the grid, and then of course after the interruption is done, the DC voltage withstand. So tests that we are going to define in IEC should cover all these stresses in an adequate way. Well, based on that, we have developed a list of test requirements for DC breakers in promotion. We focus on the fault current interruption capability. We have designed test method and test circuits that can supply stresses during all the mentioned 6 stages of current interruption. We have agreement among the 3 manufacturers of HVDC breakers on a common test program. And of course, we transfer this test experience to committees in SIGRE and IEC. Well, this is one example of a tested 350 kV circuit breaker that is interrupting hybrid DC breaker that is interrupting a current of 20 kA. And as you can see, all the stages have been fulfilled here. Well, on top of that, because we are speaking now about the external stresses that stress the circuit breaker, we did with a mock-up breaker, an experimental HVDC breaker. We looked at what are the critical stresses on subcomponents or breaker. The 3 critical subcomponents are the mechanical switching devices and their drives. All HVDC breakers have these. The other part is power electronic switching devices, and we have energy absorption devices. So it's quite important to know again what the critical components are. If you are going to set up a test program for an airplane, you need to know what the critical stresses on the landing gears are. So see it in that perspective. Well, we looked especially at the switching gaps and drives. Here in this picture, you see some illustration of how these novel switching devices in HVDC breaker under development look like. What is the key message here is that a lot of standard components like vacuum circuit breakers and disconnectors are used in non-standard way. So proper attention in test should be paid to that. Well, the other key components are the power electronic switching devices. In HVDC converters, power electronic switches, they switch all the time. In circuit breakers, they do it only in case of fault or in other case of load interruption. So a very few times in their lifetime. Well, the other new kid in the block is energy absorption devices, which means these devices need to eat up the energy out of the grid. And while normally metal oxide arresters are used for overvoltage protection, here they are also used for a large amount of energy absorption. You can read a lot of details in the papers we read. Well, this is an overview of a test of a 160-200 kV current injection type of HVDC circuit breakers in the lab. So you see it's a very large device, especially if you compare it to a standard AC breaker, 245 kV, 63 kA. You see the size of this device compared to a standard AC breaker give you some impression how difficult fault current interruption in DC is. Well, here you see the second test object. This is a 320 kV, 20 kA hybrid type of DC breaker, which was under test in the lab. Well, let me then conclude by stating that we defined a set of test requirements that covers all the stages of current interruption, and this set was agreed upon the manufacturers in the project. We applied this set to the testing of HVDC breakers up to 320 kV 20 kA. You saw that in the photograph. We made a thorough experimental analysis on experiments on internal stresses of key components, and we have transferred the lessons learned to the SIGRE working groups on DC circuit breakers. We hope to finish the SIGRE working group on DC breakers in B3 and B4 combined with A3 by early 21. We are also very actively now involved in transfer all kind of information, and also from the project in an IEC maintenance team 64, which works on a DC circuit breaker draft standards, which is hopefully going to be finished by the end of this year. And that, I think, is the last slide I would like to share with you, and I hope you have at least gained some basic information on the work that has been done, and of course for all the details you can get in touch with us.
So thank you very much, Rene, for this very good and very clear overview of both what you have been leading in promotion, and also how this has been very nicely brought already into standardization. There are two questions, but one technical question, I would say, in the chat, and this is from Cora Piccino, our former promotion colleague. Yes, Cora is asking, and you can supplement me, Cora, if I'm not getting it right, but specifically to reliability. Could all the mentioned breaker types be tested and evaluated in terms of reliability?
No. The simple answer is no. Like all